Okay, well, sometimes when we're looking at a rational function and we want to find the partial fraction decomposition because we don't recognize this from our list, occasionally we're going to see things like a repeated linear term so that we can't use cover-up method. So we're going to go through an example here where we have to do sort of the traditional partial fraction decomposition form, and then we'll do it out. So let's try this out. So here we have f of s equals negative 5s squared plus 1 over s plus 1 times s squared. Our partial fraction decomposition, the non-repeated terms just show up once, but if we're repeated, then each power is going to get its own constant on top. So we have b over s plus c over s squared. And we can figure out what a is using the cover-up method because it's non-repeated. Let's do that just to make it nice and easy. So a here, to find this, we're going to set s equal to negative 1. So this is going to be negative 5 times negative 1 squared plus 1 over negative 1 squared. That is, we have negative 5 plus 1 over 1 or negative 4. So I'm going to just include that now. And so the idea is we're going to add these fractions back together and then compare the coefficients on the right and on the left. So the denominator that we're building is going to be this one on the left of s plus 1 times s squared. So what I'm going to do is multiply each of these terms by the pieces of this denominator that we're missing on top and bottom. So if we look at the first term, negative 4 over s plus 1, we're missing an s squared, so top and bottom get multiplied by s squared. I'm just going to write out this denominator once. For this b over s term, we're missing one s and an s plus 1. So this is plus b times s plus 1. We multiply top and bottom by s times s plus 1. For c, it's c over s squared. We're missing a factor of s plus 1. We're going to multiply top and bottom by s plus 1. Okay. All right, so we now have equal denominators, and these are equal fractions, so the numerators have to be equal as well. Let's write down our expression for those equal numerators. We have negative 5s squared plus 1 equals negative 4s squared plus bs times s plus 1 plus c times s plus 1. Okay. Now we can either substitute in values if we like to. So choose a value of s, put it in. We could also rearrange things so that we have things grouped in terms of powers of s. So I see some convenient stuff going on there. So let's do that next. Here, if we group together the powers of s squared, we have 4s squared plus bs squared plus bs plus cs plus c is supposed to be equal to negative 5s squared plus 1. If we look at our s squared terms, on the left-hand side, we have negative 5 of them, and on the right-hand side, we see negative 4 plus b. Okay. Adding 4 to both sides, we get that b is equal to negative 1. Okay. All right, so this is going to be negative 1, negative 1. Okay. If we look at our constant terms, on the left side, we have 1. On the right-hand side, we see just a c. Okay, and so c equals 1. And we can always double check this, plugging in what c is equal to. Notice this bs and the cs cancel. okay, which matches the s's on the left side. Okay, so we found our partial fraction decomposition. Let's just write that out here. F of s is equal to, our value of a was -4 over s plus 1. For b, we had -1 over s. And for c, we found 1 over s squared was our term. All right, take a deep breath, and then we're going to take inverse Laplace transforms. For this first term, we're going to be using rule number 2, because we have that s plus 1 in the denominator. So here our a value is -1. For the middle term here, we're going to be using rule number 1, because we have just an s all on its own in the denominator. And for this last term, 1 over s squared, we're going to be using rule number 3. We are always going to start by matching our power. So the power of the denominator is s squared. So we see that 2. So n plus 1 equals 2. So n is going to be equal to 1 when we're working this out. What that means is that our numerator is supposed to be 1 factorial, which is just 1. Perfect, that's what we've got. Okay, so let's take some inverse Laplace transforms. -4 over s plus 1, its inverse Laplace transform is -4 e to the negative t. -1 over s, its inverse Laplace transform is just -1. And 1 over s squared, its Laplace transform. Remember, n here is equal to 1, so its inverse Laplace transform is equal to just t to the first power, or t. Great.